Good morning, everyone. It is a pleasure to be a part of this training school. I would like to thank both TÜBİTAK as well as Hüseyin Aslan Hocam for their kind invitation. I am sorry that I will not be able to participate in the winter school in person. Inshallah, next time, the next time the winter school will be organized, hopefully I will be in Istanbul and I can actually present similar tutorials in person. So my name is Murat Uysal. I am a professor of electrical engineering and also the founding director of the NYU Abu Dhabi Wireless Center. I also have an adjunct position at Özyeğin University. Also at Özyeğin, we have a Center of Excellence in Optical Wireless Communication Technologies. I am the founding director of that center as well, OCATAM. So today, in collaboration with the Professor Muhammed El Emasi from Özyeğin University, we will actually presenting this tutorial titled as Optical Wireless Communication from Fundamentals to the Future Directions. So the outline of the talk is as follows. The tutorial actually includes 5 parts. In the first part, we will start with an introduction to optical wireless. So I am aware that this winter school is mainly focusing on the RF technologies, but I will also try to explain that we are able to design high-speed, high-reliable optical wireless systems in the optical bands. These can be either in the visible light, ultraviolet, or infrared bands. And in the second part, I will also explain the transmitter and the receiver blocks for the optical communication. And we will explain that there are 2 possible architectures. The first one is the so-called intensity modulation direct detection, and the second one is the coherent modulation and coherent detection. So these 2 parts, I will be actually making the presentation, and then Professor El Emasi will take over, and he will actually talk about the channel models for the optical wireless channels, and a major performance degradation is actually coming from the fading channels, very similar to the RF. And Professor El Emasi will talk about the fading mitigation techniques in the part 4. And finally, in the part 5, we will talk about the future directions, identifying the open research gaps, and what are the perhaps some promising research directions for the new generation of the researchers who might be interested in the optical wireless. So now let me start with the introduction part. So today, when we say wireless communication, I mean, this is typically associated with the radio frequency, RF. And this is not surprising because the cell phones, the Wi-Fi modems, the Bluetooth headsets that we use today, all of them are basically using radio frequencies. But if we actually look at the electromagnetic spectrum, you immediately notice that when you go beyond the RF spectrum, you can find these very large and unregulated optical bands. These include infrared, visible light, and ultraviolet. And in principle, you can use any of those subbands for optical transmission as well. So actually, if you look at the history, you will actually find out that starting from the ancient times, the people have tried to use some type of the optical signaling, visual signaling, in order to actually achieve long-distance communication. I mean, you can think about the fire signaling, smoke signals. All these are actually kind of the primitive forms of the optical wireless. And actually, even if we come to the perhaps, let's say, 1700s, before the introduction of the electrical telegraph, we actually have seen the introduction of the so-called semaphore. Semaphore is actually defines the optical telegraph. So on the left-hand side, you can actually see this tower with the mechanical arms. So this is actually what then semaphore looks like. Basically, based on the configuration of these mechanical arms, you can actually represent some letters and numbers, and basically you will be able to transmit some text messages. These semaphores actually were built at the end of the 18th century, and especially in the France during the Napoleon Bonaparte time, they have actually extensively used it in the country, especially during their battles with the British armies. And if you actually look at the today armed forces, although they have been, of course, using much more modern techniques, still we actually see that the flex signals, signal lamps are still in use. But probably a major milestone for the optical wireless is the so-called photophone. Actually, Alexander Graham Bell invented the device, the so-called photophone, in 1880, and this was actually the very first wireless voice transmission. And as you see in these pictures, actually the setup he actually built was very simple. The transmitter was in the form of a vibrating mirror. The receiver was in the form of a parabolic mirror. And with this simple setup, he was able to transmit at a distance of more than 200 meters. And in his setup, of course, you need a light source. And the light source, in his case, was the sunlight. And in his writings, actually, Bell referred to photophone as the greatest invention he has ever made, even greater than the telephone. But of course, photophone never came out as a commercial product. And I think the reason is obvious, because obviously, as human beings, we don't have control over the sunlight. I mean, at night, obviously, you cannot use the photophone, or perhaps during the winter time when the sunlight is limited. Again, it will not be possible to utilize this device. So therefore, this never actually became commercialized. So if you want to actually implement an optical wireless system, the first thing that you need to sort out is the availability of an optical source. And now in the 1960s and 1970s, we actually see the introduction of the LEDs, light emitting diodes, and the lasers. So these are the light sources that we can possibly control and modulate. And in fact, when the lasers have been first developed, the research community thought that, okay, optical wireless communication is the main deployment area for the lasers. And as you see actually in this picture, even back in 1966, some defense companies, US defense companies, have developed these optical wireless systems for the long distance communication. But unfortunately, these optical wireless communication trials at that time were disappointing. And the main problem, because the laser beams have a very large divergence, and also the researchers at that time are not able to come up with any reliable fading mitigation technique to actually deal with the atmospheric conditions. And at that time, of course, there have been also some development in the fiber optic domain as well. And with the introduction of the fiber optic, it became the choice for the long distance optical transmission. And that basically shifted the focus away from the optical wireless systems. And if you ask me today, what is probably the most successful optical wireless communication device so far, without any hesitation, I will simply say that TV remote control. So today, even in the modern TV sets, we have actually infrared TV remote controls, and that is probably the successful, commercially successful optical wireless device. Uh, but there have been also many attempts over the last, let's say, 40 years, 50 years, to develop some optical wireless systems. And for example, in 1979, you can actually see this picture where we have an infrared optical system for the wireless transmission. Actually, if you have a careful look in this picture, you will actually find out that there are actually 4 LEDs on the corner, which is used for the transmission. And in the middle, you will actually see this photodetector. So therefore, this type of system is kind of trying to come up with an omnidirectional broad coverage. And even in the very first IEEE systems, wireless local area network specifications, we actually noticed that there was an infrared option. So the people thought that, I mean, using the infrared frequencies might be a good choice, even for the local area networks. There was also some other development of the protocols for the personal area networks, especially infrared data association at a certain extent became successful. And as you see in this picture in the this computer, you can actually see that in the late 1990s, actually some of the laptops have actually this ARDA interface for the personal area network. But later, Bluetooth was invented, and basically ARDA also disappeared from the market. So basically, I mean, as you see here, starting from the 1960s up to 200s, there have been several attempts to develop optical wireless, but for some different reasons, actually it didn't pick up. But in my opinion, this now will likely to change in the next 5 to 10 years. And that actually kind of became the motivation actually to come up with this tutorial. So to make sure that the new generation of the researchers are also aware about the latest developments. So now, before I go to the categorization of the optical wireless systems, let me also try to explain what are the main transmitter and the receiver blocks. Actually, in the second chapter, I will go into the more technical details, but at this point, I would like to give that overall picture. So in this slide, you actually see the transmitter on the left-hand side, receiver on the right-hand side. And basically, when you look at the system, you actually notice that there is a baseband DSP processing part. So this is where the modulation coding takes place. And then after the digital to analog converter, we have the optical front end. So now, if we actually compare it to a conventional wireless system operating at the radio frequencies, more or less it is the same story. It is the same architecture. We have a DSP part, and after the DEC component, DEC interface, we have a front end. Of course, in the RF systems, we are using some power amplifiers, some transmit antenna. But in this case, the front end is basically consisting of a light source, and this can take the form of a LED or laser. And you need to also probably couple them with some optics to just make sure that the convergence characteristics of light source, which is obviously affecting your coverage. And this LED or laser is basically performing the electrical to optical conversion, because DSP, obviously, the electrical domain, you actually process all the information in the DSP, and then through the LED or laser, you are performing this optical conversion, and then the light propagates through the channel. At the receiver side, you need a device which actually takes this optical signal and converts into an electrical signal for the subsequent DSP chain. And for this purpose, the conversion is actually achieved by the photodetector. So the photodetector is a device which takes the optical intensity, converts into a photocurrent, and then the rest is basically, again, very similar to the RF systems. You perform the decoding and detection. So just to emphasize that this similarity between the optical and RF systems, I would like to actually put these two block diagrams side to side, and you can immediately realize that actually the DSP part is the same. Only part that change is actually the front end. I am actually emphasizing these differences because most of the time, especially when I talk with my students, many of them kind of try to shy away from the optical wireless because they think that, oh, okay, I mean, this is not wireless. I mean, I need just like the photonics background. I cannot actually work on this domain. But once we actually understand the constraints dictated by the front end, actually the problem basically reduced to the physical layer design, right? I mean, I always define myself as a communication theory person by training, okay? So I am a physical layer design expert. And I think also in the audience, most of the researchers are coming from the physical layer design background. So therefore, if we actually have worked in the RF domain before, more or less those techniques can be applied to the optical wireless systems. But of course, what you need to pay attention now, because of the optical front-end characteristics, you need to also modify the physical layer design accordingly. So there are some additional constraints coming to the physical layer design, coming from the optical constraints. But other than that, the problem is the same. So whether it is in the RF band or optical band, it doesn't matter. We are actually dealing with a wireless system. Okay. So now, hopefully, after this general introduction, now we can actually move and try to categorize the optical wireless systems. So today, actually, if you look at the literature, you might be perhaps confused because, I mean, in different papers, actually researchers sometimes use different notations, okay? But if you want to make a rough categorization, I can simply uh, suggest the following. Let's actually divide optical wireless systems into two main groups. The first one is the so-called laser-based systems. And these laser-based systems, most of the time, are also known in the literature as the so-called free space optical communication, FSO. So these systems, FSO systems, use lasers, they use infrared band, and of course, the laser comes with an ultra large bandwidth. I am talking about the tens of gigahertz. Okay, so it is possible to design extremely high-speed systems using these laser-based systems. But of course, the laser also comes with a narrow divergence. So therefore, that means that they are mainly used for the point-to-point communication. And also, you can actually design high power lasers. That means that you will be also able to achieve long and ultra long range transmission distances. So on the right hand side, actually, you can see two pictures. The first one is actually an FSO terminal on the top of a building. So as I will later explain, you can easily connect two buildings to each other with an FSO terminal. And nowadays, we also seen the commercialization successes actually in the space domain. There are many companies which have actually started using the FSO for the inter-satellite links. Uh, but at the end, again, when you think about laser, you need to remember that you are working with a point-to-point system. But if you need broadcasting, if you need an alternative to the Wi-Fi, a local area network, then the second option will be a better choice. Those are the LED-based optical wireless systems. These are known as the visible light communication, or sometimes Li-Fi in the literature. So as the name implies, these actually work in the visible light band. They still have large bandwidth, but when I say large bandwidth, I am now talking about, let's say, tens of megahertz, perhaps like up to 100 megahertz. So this is still relatively, of course, smaller compared to the laser-based systems. And of course, the coverage area of the LED is also smaller compared to a laser. So now we will be able to support short and medium range transmission. I am talking about in the order of meters. But of course, now an LED is able to provide a wide coverage. So therefore, these can be used for the broadcasting purposes. And therefore, depending on the intended application, you can actually choose either a laser or LED to design your optical wireless system. And you can come up with an solution which can be an alternative, complementary or supportive technology to the existing RF-based solutions. So as you see here, you can actually start with the in the order of millimeters, which, for example, you can do optical circuit interconnects, and then you can move to the order of centimeters, where we are now designing body array networks, person array networks. Then you can move to the in the order of meters, now designing local array networks, alternative to the Wi-Fi. You can also design vehicle-to-vehicle systems, underwater systems. And then when you come to the long range, now I am talking about order of kilometers. That means that you can use it as a terrestrial link for the inter-building connections, or perhaps for the cellular backhaul. And then finally, you come to the space domain. You can actually design satellite links, space links, and now actually we talk about thousands of kilometers. So now let's actually try to explain these use cases. So let me start with the visible light communication first. Just remember the photophone example that Alexander Graham Bell invented. And I have mentioned that it didn't become commercially successful. And the reason was because we are not able to control the sunlight, of course, for the uh, transmission purposes. But now with the introduction of the LEDs, we have actually a light source which we can modulate really easily. Of course, the LED is used for the illumination purposes, but when you modulate it at very high speeds, actually the flicker will be invisible to the human eye. And as long as you are able to design a modulating signal with a constant average value, that means that there will be also no adverse effect on the illumination level. So therefore, I am basically claiming that we can use the existing illumination infrastructure also for the communication purposes. So this is actually the main promise of the VLC. You can use LED-based illumination infrastructure, which is already existing in our homes, in our offices, simultaneously for the communication purposes. So accordingly, we can actually divide the application areas into three main categories. And now I will try to actually motivate each of these use cases. Let's start with the wireless local area network. Of course, at this point, you can ask me, okay, I mean, you are talking about the local area networks, but we have Wi-Fi. It is extremely successful. So why do we need a light-based alternative? So let me give you some perhaps motivation points. Yes, of course, I mean, Wi-Fi is very successful and it will actually continue to be with us in the future, obviously, but it also comes with some limitations. So first of all, remember that the Wi-Fi bandwidth is shared by the users, right? So if there is only one user in a room, actually he has access to whole bandwidth. But if there are hundreds of users in the same room, then that means that now you need to actually compete for the resources. You need to compete for the bandwidth with the other users. So for example, in this picture, you see a very crowded auditorium, and if all those students at the same time try to, for example, make a video streaming, obviously the Wi-Fi will not be able to satisfy that demand. So this is what we call as the user dense environments. And in the user dense environments, Wi-Fi has actually a poor performance. And we are also aware that the Wi-Fi signals are difficult to confine to a specific area because basically there's a broadcasting nature. So as this cartoon is actually kind of pointing out, I mean, there will be some potential security implications. And also, as we are aware of, in some certain cases, in safety critical and hostile RF environments, such as refineries, nuclear plants, or perhaps in the hospital, in the intensive care units, actually RF signals, Wi-Fi is not permitted. And also, despite the lack of the scientific evidence, I mean, some health conscious people want to minimize their use to the RF devices. Even perhaps you heard about the term electro hypersensitivity. Some people actually complain about this one, and therefore they try to actually for different reasons, try to stay away from the RF devices. And even in some countries, the governments limit the use of the Wi-Fi. For example, back in 2015, the French government actually banned Wi-Fi in the nurseries and schools for the children under age 6. So all these basically limitations from the Wi-Fi side actually provide a motivation for the development of the VLC systems. And when you consider the VLC system, you can also realize that this is relatively easy to implement because most of the illumination infrastructure that we have today in the home or in the office, they actually use the LED light bulbs, right? So therefore, the LED and the power access are already available at the installation site. But what is actually the main implementation challenge? Actually, you need to feed somehow the data to these LED light bulbs, because now the LED light bulb, each of them will be basically serving as a access point, right? And now you need to feed the data each of these LEDs. So for this purpose, you can use power over Ethernet, power line communication, or of course, if the fiber optic is available, it will be the best solution, and it will be basically serving as a backhaul to the LEDs. So in the future, with the miniaturization of the transceivers, that means that these VLC chipsets will be embedded into the mobile phones. So therefore, VLC-based wireless access can be offered as an add-on service to the illumination system. So basically, in terms of the technology, there is no challenge right now. So for example, if tomorrow Apple or Samsung decides that, okay, let's put actually one of those like the VLC chipsets into our cell phones, that means that the second day you will actually have access to the VLC right away. So therefore, we actually kind of vision in the future uh, a system which will be able to operate actually different domains. So today, when you open your cell phone, actually your cell phone first scans for a Wi-Fi signal, right? So if there is a Wi-Fi signal nearby, you actually have access to it because you don't want to use your mobile data, which is very expensive. You actually prefer to use the Wi-Fi as much as possible. And if there is no Wi-Fi signal, then you actually switch to cellular as usual. So with the introduction of the Wi-Fi, what we actually see is we are providing a third option. Okay, so in the future, when you open your cell phone will first scan for a VLC-enabled LED light bulb. If there is any, you can actually connect to it. Otherwise, you switch to Wi-Fi or the cellular. So therefore, in this context, we are trying to position the VLC as a complementary solution. And also, as I earlier explained, VLC is especially attractive for the user dense environments. Actually, I am also the founding member of the IEEE standardization on the VLC. And when we actually write the standardization document, we are supposed to define use cases. And the kernel application for the VLC is these type of user dense environments. Because obviously, the Wi-Fi systems are not able to perform well in these type of dense environments. And but VLC has a much higher array spectral efficiency. So this is a key term, array spectral efficiency. We are not talking about just the spectral efficiency, but the array spectral efficiency. And obviously, in this type of environments, such as the conference halls, coffee shops, libraries, airports, actually VLC might be an attractive alternative. And as I also earlier mentioned, in some safety critical and industrial environments, VLC is also providing a alternative solution to the RF systems. And finally, RF signals are also kind of prone to the security problems. I mean, for example, especially in the military area, tactical area, that might be a big issue. But when you consider the VLC, basically the special confinement of the VLC provides an inherently secure solution. Because just imagine the Wi-Fi, the VLC signal cannot penetrate the walls, right? The light cannot go through the walls. That means that if there is any application or use case where the data security is the primary concern, then VLC is the right solution because you cannot jam or hack the VLC with the classical methods. The only way that actually hack the signal, you need like a physical obstruction. So I think that also makes the VLC very attractive for these type of secure links. And also, I want to point out that VLC is not just an academic interest, academic point at this stage. There are many companies in the world which is actually working on the development of the VLC products. So I here provided a bunch of companies, but this is by no means an exhaustive list. I am pretty sure that I missed some of them. So this is like a growing market, and we believe that in the future it will be able to get a certain market share. And also, I am proud to say that in Turkey, we have also at least one company, Hyperion Technologies, which is working on the development of the optical wireless systems. Hyperion Technologies is actually a spin-off of the OCATEM, the Center of the Excellence in the Optical Wireless Communication Technologies at the Özyeğin University. We have developed some VLC prototypes, and we have also an academic evaluation kit, which we have been able to market through the world. I mean, like many universities, I mean, in the US, in Canada, in different parts of the world, have been actually using our VLC evaluation kit. So this actually provides a easy to use, user-friendly VLC prototyping platform integrated with the software-defined radio platforms. Anyway, so now let me actually continue with some examples so that at least you can visualize what type of products are available in the market today. So in this picture, I show you the very first generation VLC products. So as you see them, these are typically in the form of the desk lamp or the ceiling light. So this is actually your transmitter. And of course, on the receiver side, as I explained before, you need a photodetector, right, to actually capture the optical signal and for the data detection purposes. So the receiver part nowadays are typically in the form of a USB dongle. Okay, so you can attach to your laptop or your mobile device. But of course, there are also some companies which are working on the miniaturization, and at least there is one company from the UK, Pure Li-Fi, which actually developed this miniaturized transceiver, and that means that now this can be easily fit into the devices as well. So therefore, if a laptop company, like a computer company, decides to put it into their devices, or perhaps like the Samsung, Apple decides to put it into their cell phones, so these miniaturized chipsets are also available in the market. And as I earlier mentioned, there have been also some standardization efforts in the VLC area. Actually, in July 2023, IEEE published 802.11bb standard for the light-based networking. And in the last year, in May, we also started working on a new version. So in this development, one of the main purposes was to make also VLC system compatible with the Wi-Fi systems, because currently it is like quite a small market, so therefore there are not so many chipset vendors which would like to invest in this area for now. So therefore, when we actually develop this standard, we actually try to use the Wi-Fi physical layer design with some sort of modifications. But in the last year's standardization, I think we will try to take a more, let's say, bold approach, because I think many companies have started realizing the feature potential, commercial value of this technology. So therefore, probably it will be kind of a more advanced version after it is completed. So now I talk about how we can potentially use the VLC for the local area networks, but it is also possible to use it for the machine-to-machine communication, because we are also aware that there is a significant increase in the number of the connected devices. So these are mainly also referred to as the IoT applications. So sometimes we use the term massive machine-to-machine communication to describe these type of systems. But of course, based on the quality of service requirements in terms of the data latency, sometimes we have also another category, the so-called mission critical machine-to-machine communication. So In contrast to these, like the low-cost IoT application, so these mission-critical devices, applications, kind of more demanding, right? I mean, I am talking about now the connected vehicles, robotic surgery, industrial robots, okay? So therefore, you need to make sure that the latency is very low, the link reliability is very high. So therefore, when you design your machine-to-machine systems, you need to also consider all these requirements in mind. And of course, there are RF-based solutions, but especially in the urban and indoor environments, IoT devices are densely deployed, and RF spectrum is heavily congested, and therefore you actually end up with the interference. But it becomes a big problem, especially in the 6G white papers. They are talking about like the billions of devices. Okay, so therefore interference becomes like a major issue. And when you actually look at the problem from the mission critical machine-to-machine systems, now that interference actually becomes a problem to maintain the reliability of the system. And of course, when you think about the RF systems, as we earlier explained, it is easy to intercept them despite the encryption. They're also prone to jamming, and that becomes also a main problem for these type of systems, especially, for example, in the military communication area, or the platoons, vehicle-to-vehicle communication. So therefore, we would like to also highlight the benefits of the VLC in these type of use cases. Basically, in the IoT applications, any device with a small LED can be potentially converted into a VLC-based IoT device. So from the healthcare to the home automation, you can actually envision different applications. I mean, I don't have much time here, so therefore I will not go into details. But I mean, this is open to your imagination. I mean, we have already published a couple of papers in this area where we try to highlight different use cases. But still, as far as I know, there is no commercial product in this market. So it might be also an interesting entrepreneurship venue. But when we come to the mission critical systems, as I earlier mentioned, now the question becomes, can we design a system with a low latency and interference free? And actually with the VLC, this is possible. So actually in this picture, you see actually a VLC-based robotic arm. So this is a pilot deployment in the BMW manufacturing facility. Actually, this was a joint project that we did before with the Fraunhofer in Germany. And this, you see those robotic arms where we actually place a omnidirectional VLC system. Actually, the resolution of the picture is a little bit, but if you actually pay attention to the top corners, you will actually see that we actually have like a cube. We put VLC directional optical links at each side of the cube. And so therefore, even if the robotic arm is actually moving, we are able to actually maintain a reliable link to the receiver side. So this is one example of the mission critical application. And another application is actually, of course, vehicle-to-vehicle communication, vehicle-to-infrastructure communication, because nowadays, most of the vehicles come with a headlight, LED-based headlight. So that means that you can use those headlights for developing a vehicle-to-vehicle communication system. And also at Özyeğin University, we have actually collaborated with the Ford Otosan, and we actually develop vehicle-to-vehicle systems. So especially those truck companies are interested in this type of technology for the vehicle platoons. And now the last application area that I would like to discuss is the underwater communication. Today, when you consider the underwater communication, the typical choice is the acoustic signaling. I mean, today you can actually purchase an acoustic modem for the underwater. So they can actually support transmission range in the order of kilometers, but their data rate is actually very low, like tens of kilobits per second. And also the latency is very high in the acoustic modems. But nowadays, we also realize that there have been some developments in the imaging systems, underwater imaging systems. So these type of systems actually use 4K high definition videos. So that means that now their data rate requirements are very high, and these cannot be handled directly with a acoustic modem. So therefore, there is a strong motivation to develop some alternative solution for the underwater communication. And that alternative solution, again, actually comes from the VLC-based systems. Of course, now you need to be also aware that all the previous systems that I have mentioned uh, are basically using white light, visible light. But in the underwater, now you need to actually switch to either blue or green wavelengths, because now at these wavelengths, the underwater attenuation is actually lower. And with a careful design, now you can actually design a VLC system which can actually achieve tens of megabits per second. But the transmission distance is actually relatively lower compared to the acoustic communication. Now, probably the maximum transmission distance that you can achieve is about, let's say, 100 meter. But you will be able to achieve quite a high speed, tens of megabit per second. So therefore, in summary, we can position the VLC as a complementary solution to the long-range underwater acoustic systems. And in the future, we envision that there will be like kind of hybrid systems which will be able to use the acoustic and optical communication systems together. And now, after the VLC, in the remaining time, I would like to talk about the free space optical communication. So, in the VLC systems, as we have earlier mentioned, we would like to use it for both illumination and communication purposes. But in the free space optical system, now basically we have just communication functionality. We would like to design a point-to-point link, and that can be actually used either as an alternative or a complementary solution to the fiber optic and RF links. So I have, I think, only 5 minutes left. So I will try to be a little bit faster in this part. So the very first application area that you can think for the FSO is the, of course, terrestrial links. So just imagine, for example, you have a university campus. You can actually have multiple buildings. Perhaps the fiber optic infrastructure is not available. And in that case, you can actually put an FSO terminal on the top of each building, and then you can actually connect these buildings to each other. And especially, this might be very useful in the urban areas separated by the obstacles such as the roads, rivers, or perhaps some other urban developments. Also, another potential use case for the FSO is the cellular backhaul and coverage extension, because obviously, especially in the urban areas, the cell size is actually smaller, right? So we have this term small cell. Sometimes, I mean, the coverage area is just like the 500 meters or even less. And especially in the urban area, it is not possible to extend a fiber optic to every point in the city. So in that case, you need some backhauling solutions, and FSO is probably providing a strong alternative to the fiber optic in these cases. And of course, if the fiber optic is not available at all, such as a rural area, isolated area, then also FSO can be a successful, powerful solution. And also, I need to highlight that FSO can be used as a temporary link in a different type of civilian applications, such as the disaster recovery, emergency response, sport event organizations. So, for example, a tragic example of the FSO deployment was after the 9/11 terrorist attacks in the US. I mean, in the Wall Street, I mean, the fiber optic infrastructure was basically damaged at that time. And just in 2 hours, FSO links were rapidly deployed by the financial corporations in the Wall Street, and they have been able to resume their operations. Another example, for example, BBC used FSO links for the live broadcasting during the London Olympics. And of course, again, in the disaster recovery, you can simply install these FSO links like with less than 1 hour, and you will be able to replace the damaged fiber optic infrastructure. And again, in the tactical field, in the military area, I think FSO is one of the best solutions, because then you don't need to worry about the jamming problem. So therefore, between the different military units, you can easily use the FSO links. And if you actually move to another area, then you don't need to actually spend time with the fiber optic installation, because nowadays in the military tactical field, I mean, as you see in these pictures, the soldiers need to actually install the fiber optic, because they really they don't want to rely on the wireless communication because of the possibility of the jamming and so on. But obviously, fiber installation takes time. And when you want to move to another area, you just need to actually do the reinstallation again. I mean, that is really challenging. But with the FSO, you now have a very flexible solution. And now the last use case I would like to highlight is the space domain. So basically, we can use the free space optics for the air-to-air communication, air-to-ground communication. Okay, and on the left-hand side, you can actually see some pictures from the pilot deployments. Of course, now when you use these type of FSO links, the design is much more challenging. Later in the last part, Professor Elemasi will talk about how we can possibly come up with some innovative solutions. Because in the previous examples, we always talk about terrestrial links. So these are actually fixed links, okay? Each transmitter and the receiver are fixed. But now I am talking about a mobile FSO link. That means that now you need to come up with the pointing, acquisition, tracking. So the problem is much more challenging, but the solutions are also available. But of course, the design is actually much more sophisticated compared to the fixed links. And the last slide I would like to talk about is the space. So as the name implies, free space optical communication is ideal for the space application, because in this case, you don't need to worry about any atmospheric effects. So the only thing that you observe, experience is the geometrical loss. So therefore, for a given distance, you can easily design an FSO system to take into account of the geometrical loss. So that means that now you can use them for the inter-satellite, ground-to-satellite, deep space applications. And actually, starting from the late 1990s, actually space agencies from the different countries have already demonstrated FSO-based solutions. However, only in the very recent days, we actually see that FSO is taking even more attention. And the reason is because now, especially after SpaceX have started using these laser links, so the space segment of the FSO market is booming. I mean, there are so many companies in the market right now working on the development of the spaceborne FSO terminals. And the most promising commercial application at the point is the interconnection of the satellite links. And as I mentioned, Starlink is using them. Amazon has been also started working on the development of their own laser links. So therefore, FSO is taking a lot of media attention nowadays. And after the introduction of these inter-satellite links, I am pretty sure that there will be also some developments for the ground-to-satellite, because now you need to actually, of course, deal with the atmospheric conditions, but there are also some powerful fading mitigation techniques that we can potentially use for that purpose. Okay, so I think I am remaining in my time limits. So thank you very much. So this actually concludes the very first part. So if you have any questions, I will be happy to take.
Yes. I just want to ask that, what about security effect of FSO when we compare to the standard or regular RF systems?
Can you hear the question, Professor?
I couldn't hear it properly. I mean, it was a question about the FSO, but I couldn't get the full question.
I just want to ask that what's the security side of
Security. So
Well-
basically, the security, I mean, we are talking about the directional link. Okay. So therefore, I mean, if you actually compare it with the RF systems, I mean, I think we actually have kind of, let's say, a robust system, right? I mean, like how you can actually intercept an directional link, a FSO link, you need actually a physical obstruction. Okay, so that is the reason that we use the term it is inherently secure. I mean, just for example, consider a vehicle platoon. So two cars are following each other. So if you are actually using, let's say, Wi-Fi or RF-based solution, okay, so basically you are broadcasting these signals to everywhere, right? But now if you are using a directional link, that means that somebody needs to actually just go and try to obstruct that signal between those two vehicles. So that is the reason that I am saying it is a physically secure system. But of course, I mean, you can also use the classical encryption techniques on the top of this physically secure solution. Any other questions?
Thank you for the presentation. I would like to ask the energy efficiency, because yesterday it was highlighted that future wireless communications needs to be energy efficient. What about the optical communications? Are they going to be energy efficient?
So if you consider the visible light communication, so you can actually realize that I am not actually designing a dedicated standalone system. I mean, you are already using the LED for the illumination purposes, and now communication becomes just like a additional functionality as an add-on service. And actually, the energy that we use for the communication purpose is actually quite negligible compared to the energy that you use for the illumination purposes. Okay, so this is the VLC case. Of course, on the FSO part, that's a different story because now we are talking about a laser. I mean, if you are actually, of course, considering a high power laser, the energy consumption must be, of course, large. Because now, for example, just imagine you are using like an inter-satellite link. I mean, therefore, according to the transmission distance, you will design the link budget accordingly. But other than that, I mean, if you have, let's say, one-to-one comparison, let's say that a point-to-point RF link compared to point-to-point FS4 link, I think either it remains the same or perhaps a little bit smaller. I don't have the exact numbers in my mind, but at least there have been some studies which actually make these like one-to-one comparisons. So therefore, in terms of the energy efficiency, we don't see a major shortcoming for the optical wireless.
I had a question about the standardization aspect. So you mentioned there was 802.11bb and now I think VR which is going on. And one of the initial goals was to look at the compatibility with Wi-Fi. So is VLC primarily going to be, let's say, paired with Wi-Fi? Are there any, is there an independent standard that we can expect? Or the products that you mentioned, so are they also following that Wi-Fi standard or are they independent of that?
So I couldn't get the full question because there is some distortion, but I think the question was about the standardization about the VLC and how it is compatible with the Wi-Fi. Am I right?
Yes.
Okay. So actually, to be honest, I mean, this standardization effort is a long story. I mean, I have been actually involved in this standardization work from the start. So to be honest, I mean, like when we first started the big companies, I mean, in the IEEE standardization, like the Intel, Qualcomm, the big guys, I mean, they were very skeptical. So that was the reason that even we couldn't initiate the standardization under the 802.11. Okay, so we need to first start work with the 802.15. So that was, you know, the home of the Bluetooth, like the personal area networks. But over time, I think over the 2 years, we have been able to convince those big guys that, okay, I mean, so this is an emerging technology. It has a certain promise. And I always try to explain that we are not trying to kill your business. Okay, I mean, we know that Wi-Fi is mature, Wi-Fi will be with us. But you should also realize that there should be some certain application use cases where the Wi-Fi, unfortunately, is not giving the best performance. So as VLC systems, as VLC researchers, we are trying to actually focus on those type of application and use cases. And eventually they agreed that, okay, I mean, this can be a part of the 802.11, which means that home of the Wi-Fi, okay? But after we actually work on the standardization, while we are working on the standardization, I mean, of course, now the question becomes, how big is the market, okay? So unfortunately, none of those like the big vendors are willing to make a big investments on a relatively smaller market. I mean, so because think about the Wi-Fi market, it's a huge market, like billions of devices. And now when you talk about VLC, perhaps let's say, I don't know, thousands, hundreds of thousands, but still, I mean, for a big company, this is a small market, okay? So therefore, although, for example, in the physical layer design, you can actually come up with many sophisticated solutions, they simply insisted that let's actually come up with a solution which will be building on the OFDM, okay? So therefore, they will actually willing to take their Wi-Fi chipsets and make some small modifications, but they didn't want to actually come up with a dedicated manufacturing line. So therefore, if you go and check the 802.11bb, the very first VLC standard, you will immediately realize that it is a very simple modified version of the Wi-Fi standard, and that request actually came from the those like the semiconductor companies, okay? Because they just wanted to taste the waters. They would like to just understand how the VLC will be evolving. But I think in the new standard, I mean now, as I try to explain, we can have a more perhaps like a bold approach. We can probably come up with some better sophisticated techniques. But I mean, time will show, I'm like, what will happen. But again, I mean, the reason that they wanted to make it very similar to the Wi-Fi physical layer because of the just at that time they see the commercial market size relatively small.
Thank you for your presentation, Professor. My question is about Wi-Fi. You said that existing infrastructure can be used, such as LEDs and light bulbs, as transmitters, but what about uplink?
Yeah, that's a good question. I mean, in the uplink, for example, in the standardization, we simply say that we will be still relying on the Wi-Fi if available. Otherwise, we need to probably work with an infrared solution because in the uplink, obviously, I mean, using like a visible light is not a user-friendly solution, right? I mean, so actually in the picture, you have seen the very first generation VLC products. The receiver is actually in the form of a USB dongle, right? I mean, probably as an end user, you will not be very happy to put like a visible light transmitter, right? I mean, it will not be user friendly. So therefore, in the standardization, we said that either you can use the Wi-Fi if it is available. If not, because perhaps it is restricted, RF restricted environment, then in that case, you need to use an infrared system.
Thank you for your presentation. I have two questions. One, what are the upper limits of the user equipment or users for the Wi-Fi? Because you mentioned it can be also served for the IoT scenarios. Second one, do you have any concerns about the quality of service during the, for example, the peak crowded areas? What are the upper limits for one user? Thank you.
So when you mention upper limit, you are talking about the upper limit on the data rate, you mean, or?
Yes, that's basically
okay. So in the actually today you can actually design a VLC system using the off-shelf LEDs. In the second chapter, I will actually explain that. I mean, if you purchase an LED and you actually measure the bandwidth, I mean, Depends on your luck, okay? I mean, it can be just a few kilohertz, it can be perhaps a few megahertz, okay? Because nowadays, obviously, all those LEDs have been designed for the illumination purposes, right? I mean, no company is actually designing an LED for communication purposes, right? So therefore, the bandwidth of the LED is actually kind of a bottleneck here. But you can actually design pre-equalization techniques. You can use some tricks in the front end, and you will be now able to improve the bandwidth of that LED, commercial off-the-shelf LED, to the tens of megahertz or even like the hundreds of megahertz. Okay, so if you have like the hundreds of megahertz, even if you are using binary signaling, that means that hundreds of megabit per second. If you go to the advanced modulation techniques, optical OFDM, now with the QM or PSK, that means that you can easily hit the gigabit per second.
Thank you, Professor. We ran out of time.
Okay, so shall I continue with the second part or? Thanks so much. Shall I continue with the second part or are we having a break?
We can continue.
Okay. Başlayabilir miyim? Biraz bekleyeyim mi?
Başlayalım Murat. Murat başlayalım Murat hocam.
Tamam. Okay, so in the second part, I would like to talk about the optical transceivers. So therefore, we are going into a little bit more technical details. So as I already mentioned, if you want to design an optical wireless system, as a transmitter, you have two choices, LED and laser. So actually in this part, first, I would like to talk a little bit about these two options. What are their differences, major differences? And then at the receiver side, you have the photodetectors. This is actually the main component of the optical wireless receiver. So I will also try to explain what are the main limitations on that front. And then we will actually put all these things together and we will try to explain what type of architectures we can actually come up with. And actually in the optical communication, we will actually find out that there are two options. The first one is the intensity modulation and direct detection. And this is the obvious choice for the non-coherent light sources, such as the LED. But if you actually have a laser, that means that now we have a coherent source in your hand. That means that similar to the RF systems, you can also design coherent modulation and detection. So now let me actually start with this comparison of the laser and LEDs. So here I actually try to identify the main characteristics, including the output power, spectral width, modulation bandwidth, electro-optical conversion efficiency, directionality, and so on. And now if you actually want to make one-to-one comparisons, you will immediately realize that these two optical light sources are quite comparable to each other. So let's start with the power. Obviously, the output power of the LED is quite low. So that also explains that why we actually use the LED mainly for the short and moderate transmission ranges. But when you talk about a laser, I mean, you are able to design a intersatellite link, right? I mean, thousands of kilometers, because we have actually high power lasers. So therefore, you will be able to overcome that geometrical loss. And also, when you look at the optical characteristics, the optical spectral characteristics, the LED, you realize that it is kind of occupying a large width, but the laser is kind of a more narrow characteristics. But of course, I mean, optical spectrum is only one side of the coin, because when you design a wireless communication system, what is important for you is actually the modulation, electrical bandwidth, right? Because that is where we are able to use for the data transmission purposes. And for the LEDs, as I tried to explain in the response to one of the questions, basically none of these LEDs are manufactured for the communication purposes at the first place. But I mean, you are able to somewhat improve the modulation bandwidth using pre-equalization techniques and some tricks in the front end. And therefore, you will be able to achieve, let's say, tens of or hundreds of megahertz. But on the other hand, the laser, by its nature, comes with a large modulation bandwidth, and it is very easy to have a laser of tens of gigahertz. And in terms of the electro-optical conversion efficiency, I mean, in the LEDs, this is typically small, but the laser is much higher. In terms of the directionality, obviously LED, it has a broad coverage, okay? So most of the time we model the LED as a Lambertian source, which is actually kind of providing transmission to every direction. On the other hand, a laser is a highly collimated device, but also that gives us an advantage when you design a point-to-point link. And in terms of the coherence, and that is probably the most critical part, which eventually affects the design of the communication system, LED is a non-coherent light source. That means that you don't have like the phase information. But on the other hand, in a laser, we are talking about a coherent light source that actually gives us the opportunity to design a coherent receiver as well. Perhaps it is challenging, but it is possible. And I will also explain them later. And in terms of the cost, of course, LED is quite low cost. I mean, we are using it for the illumination purposes anyway, but the laser is actually, of course, coming with a higher cost. So now let me actually go into a little bit more details about these differences. So let's start talking about the bandwidth. So now assume that you want to design an FSO system. So we have an infrared laser. So if you want to keep your design cheap, low cost, I can suggest that go and directly modulate the laser. Okay? So you don't need an external modulator actually for the modulation purposes. I mean, the design of an FSO system can be as simple as, for example, in the labs, communication labs, in the undergraduate labs even, we are using these software-defined radio platforms, such as the Adam Pluto, right, from the analog devices. You can simply take an Adam Pluto, generate your waveform, and then you can feed a laser. That's it. But now the question becomes, how fast the electrical current coming from the Adam Pluto to the laser will be able to modulate this device? Because after some point, the laser might fail to respond to the current variations. Actually, this is determined by the so-called modulation bandwidth, or the electrical bandwidth. So actually, in this picture, you can actually see the frequency response with respect to modulation frequency. And you can actually immediately realize that the lasers, even with the direct modulation, they have a modulation bandwidth of tens of gigahertz. Okay, but the exact value depends on the DC bias, and according to the DC bias, you can actually kind of like the fine-tune the achieved bandwidth. On the other hand, when you come to the LED modulation bandwidth, that's a different story. So why do we have actually much lower bandwidth compared to the laser? Actually, that requires to understand how we are generating the white light. So to generate the white light, basically we have two options. The first option is actually you take a blue LED and then you cover it with a yellow phosphor, okay? And that actually generates the intended white light out. So if you consider the blue LED, I mean, the response time of the blue LED is quite fast, around 20 megahertz. But then when you cover it with the yellow phosphor, that phosphor actually kind of limits the frequency response. And now, if you go to the other option, which is the RGB, red, green, and blue, you mix them together, and then you are able to generate the white light. But even in that case, then you are still limited to the less than 20 megahertz. But as I mentioned a couple of times before, with the pre-equalization, I mean, we also have achieved like the very similar results in our lab as well. You can very easily achieve modulation bandwidths on the order of several tens of megahertz, even up to 100 megahertz and more. And when I say pre-equalization, the idea is the following. First of all, you need to check the frequency response of the LED, and then you need to pre-equalize it. You need to design a pre-equalizer to extend that response of the LED. So this is actually what we do at the transmitter side. And now, when you design the optical wireless system, another thing that you need to pay attention is the input-output characteristics. Actually, this is kind of similar, perhaps, I mean, to the power amplifiers that we are using in the RF systems. So now, in the optical wireless system, obviously, for the electrical to optical conversion, we are using either an LED or laser, and therefore you need to also pay attention to the input and output characteristics. So now, on the first picture, you can actually see the LED input output. So the x-axis representing drive current, and the y-axis is representing the output power. And as you see in this picture, there is a linear region followed by a saturation region. So therefore, when you actually turn on your light, that means that it is operating with a certain DC bias. So if that DC bias is actually close to the saturation region, I mean, for the illumination, that will not actually be a big problem, right? I mean, because, for example, if you want to have perhaps higher output power, you can actually perhaps prefer to work actually near to the saturation region, because more drive current, that means that more output power. However, when you design a communication system, especially let's assume that you are using optical OFDM, you are using, let's say, 16 QM, 64 QM. So the peak to average power ratio is obviously high, okay? And therefore, if you are actually operating close to the saturation region, then you will, of course, end up with some distortion. So therefore, when you actually design your VLC system, you need to make sure that you choose your DC bias within the dynamic range of the LED, the linear region, to avoid any distortion. And in the second picture, you see the laser input-output characteristics. Of course, the characteristic is kind of different. So typically, we work on the right-hand side. So this is like where we have more or less like a linear relationship between the drive current and the output power. But since I'm in the laser-based systems, illumination is not an issue. You really don't need to worry about those type of things. I mean, because you don't need to kind of come up with a trade-off between perhaps the illumination and the communication purposes. So therefore, you have kind of more flexible in the system design. So now, so far I have been talking about the transmitter part. So if we actually come to the receiver part, now you need a device which actually takes the optical signal and converts into an electrical signal for the DSP part. So for this purpose, we use the so-called photodetector. So photodetector is basically an optoelectronic device. And in terms of the mathematical model, most of the textbooks actually use the so-called photon counting. Okay, so they say that a photodetector can be modeled as a photon counter. So therefore, there is like a number of incident photons, and then based on the that conversion efficiency, we actually try to find out like how many photocarriers are obtained at the output, and accordingly they calculate what is the electrical current which has been generated. Of course, if we actually use this photon counting approach, okay, that's a nice abstraction, but that doesn't actually take into account the bandwidth. They simply assume that there is an infinite bandwidth. But of course, in our case, when you design a communication system, the bandwidth is one of the main design criteria. So therefore, we suggested you use like a low-pass electrical filter in your model. So therefore, you actually take into account also the finite response time of the photodetectors. But I also need to emphasize that if you look at the transmitter side and the receiver side, most of the time, our bottleneck is actually the transmitter, okay? Because the photodetectors the available photodetectors have already quite large bandwidths. So most of the times, that doesn't become a bottleneck for the system design. For most cases, 99%, the bottleneck is actually the LED, for example. So now, after we actually get this photocurrent, the electrical current, then the rest is again just the DSP, very similar to the RF systems. But of course, if you are a communication theory person and you would like to kind of use this photodetector for the performance analysis, you need to also understand the type of the statistical characterization. And basically, if you look at the output of the photocurrent, you actually realize that this is Gaussian distributed, okay? Basically, the output of the photocurrent is, there is a DC component, and that part actually carries your signal. And actually, around the mean, you find out that there are some fluctuations, and that come actually from the randomness of the photodetection process, how those like the photocarriers are actually generated by the detection. So basically, this noise term is modeled by the Gaussian, as you see, kind of the classical assumptions that we also use in the digital communication systems. Therefore, the performance analysis is kind of more or less the same. Like you can come up with some Gaussian Q functions if you would like to understand the performance characteristics. And here you need to also, of course, in your calculations, need to pay attention to the responsivity of the photodetector because the received optical power is basically the optical intensity. Now in the electrical domain, we typically, of course, like work with the power. So therefore, please make sure that you also make this conversion. Especially in some papers, we noticed that, especially for the newcomers from the RF domain, they don't really realize that this optical power is simply corresponding to the electrical current, okay? So therefore, you need to actually take into account this conversion in your performance analysis and analytical framework. And basically, there are different ways to model the light wave signals. So therefore, when I actually talk about this photocurrent or photodetection process, basically I am approaching the problem from the photon optics perspective. But also in many other textbooks, they also use the wave optics. Basically, at the end, they actually come to the same conclusion. But how they do it is first they start with an electromagnetic wave. They actually do the calculations to calculate the optical intensity, and the power actually becomes just an integration over the photodetector area, because every photodetector actually comes with an aperture size, and the resulting power, optical power, is basically calculated through this integration over the aperture area. But at the end, like these two expressions, of course, whether you are using wave optics formulation or photon optics formulation, the answer will be, of course, the same. So now, after we are able to actually provide these basic descriptions of our transmitter and the receiver, now I think we are ready to move ahead, and I can now describe our two architectures. So the first option we have is the intensity modulation and direct detection, IMDD. And to be honest, I mean, I have been actually working in the optical wireless area, I think now for more than 20 years. So when you look at those earlier papers, actually in the 2000s, you immediately realize that all those papers assume IMDD. I mean, whether it is LED or laser, it doesn't make a difference. I mean, all those earlier papers focus on the IMDD. And the answer why we actually assumed IMDD in those earlier works, because it is easy. It is very easy to implement. In the IMDD, information is simply encoded by changing the optical power of the source, okay? So you are basically changing the optical intensity. And at the receiver side, you don't need a coherent detector. You don't need a local oscillator, right? Especially, of course, in the case of the LED, you don't have such an option. But if you actually assume a laser, still direct detection is much easier because I am simply using a photodetector which takes these optical intensity variations and converting into an electrical signal. And therefore, it is also the same reason if you actually, for example, purchase an FSO system today, a terrestrial link for terrestrial links, all of those systems are using IMD. But now, when you come to the second architecture, coherent modulation and coherent detection, I mean, here probably most of my audience today is actually coming from the RF background. I mean, these are obvious options, right? In the RF systems, in the wireless systems, we typically use the coherent techniques. But you need to also realize that this is not very easy to implement in the optical communication. Because now, very similar to the RF systems, we claim that we will be using amplitude, phase, or the frequency. Okay, that's good. But that means that now at the receiver side, you need a coherent detection. Coherent detection requires a local oscillator. And the local oscillator, in the context of the optical systems, means that another laser. So just imagine the difficulty of designing a system. I mean, there is an incoming optical signal, and then you are trying to actually mix it with another laser. Of course, this was quite challenging, but now it became feasible in recent years. I will also tell about those details in the coming slides. But now let's start with the IMDD. So actually, if you are using a LED as your light source, it is non-coherent. So therefore, for the VLC systems, the only option you have in your hand is actually IMDD. Okay. On the other hand, as I earlier explained in the first chapter, FSO systems use lasers. These are coherent light sources. But therefore, it is also possible to use the coherent modulation and detection if you will. But again, because of the simplicity and the cost, historically, even for the FSO systems, IMDD became the typical choice in the commercial links. So today, actually, coherent FSO systems are available, but mainly in the space domain for the satellite links. But still, to the best of my knowledge, there is no commercial FSO link for the terrestrial applications, which is working on the coherent architecture. So now, in the IMDD systems, you actually have two options for the modulation. Either you can directly modulate the laser. So as I earlier mentioned, it is simply putting a DC bias on laser, and on the top of the DC bias, you are imposing your message signal. It is simply a time varying current on the DC one, and then the optical output is being generated. So this is very straightforward. And of course, when you have such a system in your hand, what you need to pay attention that we are modulating the intensity of the optical emitter. So therefore, the resulting signal should be real valued and non-negative. So in that case, what type of modulation techniques you can choose? The source and obvious choice is actually the pulse modulation techniques. So as you see on the right hand side, I mean, you can go with your favorite pulse modulation technique. It can be pulse amplitude modulation, pulse place modulation, pulse width modulation. You can name it. And according to your use case, you can actually prefer one of those. However, as Professor Elemasi will be explaining in the third part, when we actually look at the channel characterization, we will actually find out that in the VLC systems, we actually kind of end up with a multipath propagation. Because just assume that there is an indoor environment, there is a ceiling light, and the ceiling light is now your VLC transmitter. So therefore, it is possible that VLC signal is coming to the receiver following a direct line of sight path, but there might be also possible of some refractions, right? So the light might be actually refracting from the, let's say, top of a table or from the other objects. And therefore, you will actually find out that in the third chapter, the VLC channel is actually kind of multipath nature, and the delay space is on the order of 10 nanoseconds. But furthermore, in that channel, most of the time we work with the so-called effective channel, right? We don't only look at the propagation channel, but also you need to also look at the front-end characteristics. And most of the time, the low-pass characteristics of the LED further limit the modulation bandwidth. So combine these together, we basically end up in a frequency selective channel, especially when you want to achieve high data speeds, gigabit per second in the VLC systems. And from the RF systems, we are aware that an efficient multi-carrier approach to mitigate the inter-symbol interference in the case of the frequency selectivity is the OFDM. And typically we use the OFDM with the PSK and QM. And the idea is obvious. You actually have a high rate data stream and you actually transmit these over a number of frequency subcarriers. And if there is enough separation between them, then you can take advantage of this orthogonality, and we will be able to maintain frequency flat channels for each of them. But now the problem is, if you want to apply this OFDM technique to a VLC system and IMDD system, then you need to also make sure that the output is actually complex and the bipolar. Because in the output is actually real valued and unipolar. Because if you look at the conventional OFDM designed for the RF systems, if you look at the IFFT output, we know that IFFT output is actually complex value, right? And it can take both positive and negative values. But in the VLC systems, you need to make sure that the output is real valued and it is also non-negative. So that is the reason that in the literature, we have actually proposed different modified OFDM systems. And I would like to highlight two of those in this slide. The first one is the so-called DC bias optical OFDM. The second one is the so-called asymmetrically clipped optical OFDM. And also this DC bias optical OFDM is actually the physical layer which has been also used in the IEEE standardization on the VLC. Actually, in both techniques, to obtain the real value signals, the trick that we use is the same. We actually apply Hermitian symmetry on the data frame. So if you look at this data frame, you see that on the left-hand side, I have my signals x1, x2, x3. And now on the right-hand side of my data frame, I am imposing my Hermitian symmetry. So what happens when you look at the output of your IFFT output? Now we actually end up with a real value signal. And in the ACO FDM, it is kind of the same trick. We are using the Hermitian symmetry again. But we are not done yet. Why? Because yes, it is real valued, but still it is possible that they can take both negative and positive values. So you need to also come up with another trick to actually overcome this problem. In the DCO OFDM, actually the trick is straightforward. We put a DC bias, and perhaps that DC bias is actually higher than the DC bias required for the illumination, and then you actually shift it to the dynamic range of the LED, that linear part. In the ACO FTM, actually they are using another trick. We are modulating only the odd carriers. So if we actually return back to the previous page, you see that I mean, we have the x1, x3, but then these are just for the even value subcarriers. But for the odd value subcarriers, I am simply inverting 0. So how does it help us? Basically, by using this trick, we are able to obtain a symmetry in the time domain. So as you see in these two figures, then because of this symmetry, you can actually clip the negative parts without any loss of information. So at then, with these modifications, we have been able to obtain a real value signal and unipolar. So that means that now you can use OFDM in the IMDD. You can send PSK or QM signals, and therefore you will be able to maintain, of course, like a higher spectral efficiency compared to the pulse modulation techniques. So now let's come to the receiver side. We talk about the modulation techniques. I have explained that you have two options in your hand. Either you can use pulse modulation or with some certain tricks, OFDM, multi-carrier techniques. For the direct detection at the receiver side, actually, it is just a photodetector followed by a transimpedance amplifier, and that's it. Very simple, very low cost. But of course, I mean, in the practical implementation, some additional problems arise which you need to be aware of. Because when we actually model the photodetector, I simply talk about the shot noise. Yes, shot noise actually arises from the photodetection process, but most of the time the bottleneck is not the shot noise. The bottleneck becomes actually the background noise and the thermal noise. Background noise is extremely important because now these are coming from the background radiation from the ambient light. Okay, so for example, in the indoor systems, I mean, background noise is typically not a problem. But for example, if you want to design a vehicular VLC system, two vehicles are communicating with each other. That means that you are actually in the outdoor. You need to actually face also the sunlight. And therefore, you need to actually come up with some certain solutions. It can be filtering. It can be, for example, adjustment of the field of view to make sure that the background noise is actually limited in your system. Otherwise, you will actually end up with the saturation of your system and the system will be failing. And of course, there is also like the thermal noise, like the classical because of the front end. But most of the time, the background noise is becoming the major limitation. But in terms of the performance analysis, all of them are Gaussian in a way, but the background noise becomes the limiting factor. And now, so far, I have been actually talking about the direct modulation. As I earlier mentioned, direct modulation is easy. Most of the lasers can actually go to the gigabit per seconds. But when you actually increasing the data rate, there is kind of like this some certain limitations arising from the direct modulation. This is what we call is the kind of the frequency chirping. That means that instantaneous frequency of your laser output change actually with time. So therefore, that actually kind of motivates the use of the so-called external modulation. In the external modulation, now you have an additional device next to the laser, and that external modulator is of course provide, let's say, more reliable output. But of course now it comes with an external cost. It will be kind of more expensive than the direct modulation. I mean, we don't have much time left, so therefore I will not go into the details of the modulators, but basically we have two options, either electro-absorption modulator or electro-optic modulator. Especially electro-optic modulators are the common choice in the market today. Most of the time we work with the so-called Mach-Zehnder modulators, MZMs. So with the MZM, you can actually use by adjustment of the voltages, and they actually give like a very easy way to modulate your signals externally. Okay, so in the remaining time, let me actually move ahead with the coherent detection. So coherent detection is, as I already mentioned, I mean, has been already used in the RF systems. So if you want to design an FSO system, since they are using laser, it is also possible to use the coherent modulation and coherent detection. So that means that ASK, PSK, FSK, QM, whatever your favorite modulation technique, it can be also used for the FSO systems. But now, again, the receiver part is actually the most critical one, because now you need actually a optical oscillator. And that was actually the reason these coherent architectures have been delayed for a very long time. Because in the past, most of the time, the people have been trying to use like some optical domain solutions. Because later we will actually discuss the block diagram, you will see that as a local oscillator, I am using another laser. And obviously, to make sure that this incoming laser signal, optical signal, receive signal is actually matched to the local oscillator is a big challenge. There will be like a huge phase noise, for example. How you deal with the phase noise? In the past, the people have been trying to compensate it through the optical domain techniques. So basically, let's assume that you want to design an optical PLL, optical phase lock loop. This is extremely difficult, okay? And that was the reason that they were not able to come up with a robust solution, robust product. But in the last 10 years, there have been very significant developments in the fiber optic area. And nowadays, coherent systems became default choice for the fiber optic systems. Okay, but if you actually look at the latest fiber standards, I mean, they are actually using the coherent techniques. And how are they able to achieve these type of performances? Because now the DSP is very strong, so they don't need to actually deal with those type of phase impairments or other distortions in the optical domain. They actually postpone all those type of impairments to the electrical domain, and they are actually taking advantage of the powerful DSP solutions. So that is actually the key answer why actually coherent solutions now became a default choice for the fiber optic systems. And now we actually see a similar trend in the free space optical systems. Although all the earlier works they've been using the intense modulation direct detection, now we see a trend towards the coherent FSO systems, and the very first commercial FSO systems, coherent ones, have been already deployed in the space. So now, if you want to design a coherent system, you have two options. Either you can go with the heterodyne or homodyne. So this depends on the choice of your local oscillator frequency. And these are the same terminology that the RF people are using. So in the homodyne coherent detection, that means that the local oscillator frequency should be selected the same as the receive signal. In the heterodyne detection, now there is kind of the two conversion stage. So a second down conversion is required to retrieve the message signal. And another categorization actually comes from the so-called, if you want to use a single branch or balance approach, which will be explained in the next slide. But let me actually first provide the single branch version. So this is like of course, like conceptual design, very simple, but I think it will give actually the big picture. So assume that you want to send like a real valued baseband signal, ASK or multi-level ASK. So now R of T is my receive signal. I am using a combiner, and in practice, it is basically a beam splitter, but I am actually used in the reverse version. And now there is an optical signal, optical local oscillator. So that means that another laser. So you actually combine them together and apply to a photodetector. And basically, when you actually look at these, like the R of T and local oscillator signals, I am using these complex exponentials, and I am assuming that they are operating at the same frequency, but there is kind of a certain phase shift between them. So the output of the photodetector after the combiner is given by the following. So this is actually the photocurrent. So you see that it includes three terms. The first one is actually includes my receipt power multiplied by the responsivity of the photodetector. The second one is the responsivity multiplied by the local oscillator power. And of course, because of the propagation path, the receipt power will be much smaller than the local oscillator. So therefore, the first term can be ignored. And then this third term is actually where my message signal is hidden, right? Because the message here is represented by the AM, and the P of T is your pulse shape, and there is also kind of a phase impairment. And so basically, you need to do detection and try to retrieve this message signal AM from these equations. So the second term can be also removed because of the capacitive coupling from the photodetector to the front end electrical amplifier. And now in the remaining term, in the third term, you can basically compensate this phase difference either using an optical PLL, but again, as I explained, this is very difficult to implement and typically we don't use it at all. Or you can just use some DSP-based post-correction techniques in the electrical domain, which is much, much easier. So, of course, in the previous example, just to make sure that it is conceptually simple, I just use here binary PSK or multi-level ASK, okay? So it was a real valued baseband signal. But now assume that I would like to extend this discussion to the PSK or QM. So now, of course, I am dealing with a complex valued message signal. And again, you can either design like a single branch or balanced photodetector. But again, in order to keep the discussion simple, I am assuming single branch system. Okay, that means that I am using only one photodetector for each of those branches. So this is what an optical IQ coherent receiver looks like. So the receive signal is coming, and we then actually split them into two. And basically, the first branch is the I branch, the second branch is the Q branch. And again, we have a local oscillator, which is another monochromatic laser. From a splitter, I am actually taking my two signals, and I am also applying that phase shift. And these are applied to the beam combiners. Again, in the practice, this is basically a beam splitter, but in the reverse direction. And then at the output of the beam combiner, we have our photodetectors. And we can basically do similar mathematical derivations to obtain the I branch and the Q branch. So then the rest actually becomes just a DSP. So actually, again, one message that I emphasized earlier and would like to repeat again. Basically, if you look at the architectures of the optical systems, you will actually realize that, especially nowadays, everything is in the DSP domain because the IQ coherent receiver that I just explained is simply the optical front end. But then after this optical front end, like you have the transimpedance amplifier, ADC, and then the rest is simply DSP. So in the DSP, you can use your demodulation techniques, you can use like the post-equalization or any type of the distortion coming from the channel or the front ends can be also dealt by the DSP algorithms. And for example, at my university in Abu Dhabi, we have already implemented like an end-to-end coherent optical system. We have been able to achieve 250 gigabit per second. And I was really amazed that like how the things are straightforward because most of the algorithms that I am using for the post correction are actually coming from my previous algorithms that I also use in the RF systems. So once again, perhaps the name is optical, but the principles for the wireless systems remain the same. So basically, that concludes the second part. So I will be happy to take any questions.
We said that the coherent receiver solves the problem of IMDD with constraining the phase. But still, if I understand right, still the sensor, I mean the front end of receiver is same. So we do not get the exact waveform, right? If so, how we use the local oscillator in the receiver? By the way, can you please share the block diagram of single branch Alex? My question relates to that one.
Just a moment. According to this picture,
The next one. Yeah, that's one. The PS power split is different from the photodetector because the same way we do not get the exact waveform. The phase information doesn't probably inside the RT. Is it so? If so, how we use the local oscillators to compensate the phase? Yeah.
I mean, we are not compensating the phase. I mean, as I tried to explain, I mean, there is a phase difference here, for example. Okay. So, because these are independent sources, okay? I mean, so there is an incoming signal. So, the incoming signal is actually generated by the transmitter, and obviously it is possible that there are some additional phase imperfections coming from even the channel, right? So, there is a incoming signal. So here the phase, for example, pi c is representing your incoming phase. And there's a local oscillator. And that local oscillator has also totally independent at the same frequency. Okay. So now the question becomes, after you actually make this like the combining process after the photodetector, you see that that phase difference is still available, is still appearing in your equation. So therefore, you need to find a way to actually compensate its effect. And what I am suggesting that instead of working in the optical domain, actually compensate it in the electrical domain. Okay, so just use some DSP techniques.
My question was not related to that. In IMDb, you thought we still looking for the energy in the signal. So again,
Okay.
the system in coherent receiver, we again look for the energy. I mean, at least you told.
We are not looking at the energy. I mean, so here we have also access to the phase information.
I'm asking how we are.
Okay, I mean, so as you see, I mean, like in the expressions, I mean, probably your misunderstanding actually comes from the fact that we are using a photodetector. Okay, but if you actually look at the expressions, you will actually immediately realize that the phase information is still there. Okay, so I mean, if we actually go and use PSK or QM, okay, that means that I have both the phase information and the amplitude information. Okay, I didn't actually provide the detailed derivation steps here because it's quite long. It takes like the 3 or 4 pages, but you will be able to track your phase signal at every point. And at the end, when you actually look at the final expression, you will see both the amplitude of your message signal and the phase of your message signal. Okay, so therefore, coherent architecture is able to preserve both the amplitude and the phase information of your message signal. Okay, I mean, I will be happy to provide additional references and my derivations if you like to see. Okay, but once again, I mean, in the coherent system, we are not just looking at the intensity. We are able to preserve the phase information.
What kind of laser system you use in the local oscillator? Because it seems, for modern detection, especially, the laser local oscillator should be very fine-tuned or even certain distances not tunable. We use those kind of lasers in atomic clocks and also gain pulses in quantum computers, but they are very expensive. So I'm wondering, you know, is it financially, is it feasible to implement such local fine-tuned oscillators?
Orkun Hocam, I mean, I couldn't actually hear the whole question, but I think it's about the polarization, as I understand, right? You ask about the
Oscillator, you know, very fine-tuned for homodyne detection. What kind of local oscillator is used? Because they are
okay. So
really
in our experiments, we are using actually a optical IQ modulator from the Fraunhofer. I think they are using DFB lasers, okay, as far as I remember, in the architecture. Of course, I mean, the spectral width should be sufficiently small. Otherwise, I mean, like it becomes like a real problem in the detection part.
not only I think the spectrum bandwidth is small, but also I think phase coherence, right, is also important.
Exactly, hocam. I mean, that's a very big issue. But again, in the DSP domain, I mean, as long as you have some talented DSP engineers, I mean, most of the things are easily handled nowadays. I mean, it is really amazing. I mean, because when I first look at the distorted signal, I mean, I thought that, okay, I'm like, how we will be able to handle those things. But then with the enough DSP power, I mean, those things are relatively easier nowadays.
And if that's possible using post-processing at DSP level, that may have a lot of applications in quantum computation, also atomic clocks as well, because it's a very big issue, you know, to have a phase coherent and tunable lasers.
Yeah, exactly, hocam. And nowadays we are looking also like the AI-based solutions for the DSP part, because especially when you work with the like the nonlinear front ends, you know, to find the optimal solution is quite challenging. But now I mean, most of the time when you are working on the mathematical formulations, we go to some approximations, and so therefore you are kind of deviating from the optimal solution. But with the AI and machine learning, I mean, they are giving like kind of truly optimal solutions for us. So therefore, one of the research directions that we are looking is basically AI-based designs for the coherent FSO systems.
I want to ask you a question about the sunlight effect of the receiver sun. What are the limits of the sunlight density or temperature on the receiver side in terms of noise figure or signal to noise ratio, like sunlight density or temperature?
I am sorry, I mean, like, because of the microphone, I mean, there is a lot of distortion. So most of the time I am not able to understand the full question. So I said I heard the sunlight and the noise, but
yes, in receiver side, what are the effects of the sunlight?
Sunlight, okay. Sunlight is actually one of the big problems, especially for the outdoor systems, okay? But one thing that you need to pay attention, sunlight, of course, I'm like, when it goes through the photoreactor, it is also generating a photocurrent, but it is unmodulated signal, okay? So since it is unmodulated signal, basically its eventual effect is just like a higher DC bias. So therefore, when you actually remove the DC bias, some effect of the sunlight has been already removed. The second effect of the sunlight is it is, of course, introducing some additional fluctuations on the top of your received signal, and that part becomes actually kind of a limiting factor in your signal to noise ratio. Okay, but what I can say is with a field of view, I mean proper field of view, you will be able to kind of minimize the incoming sunlight. So that will be able to somewhat help you to, let's say, mitigate the effects of the background noise. But most of the time, in our experiments, we are able to deal with the sunlight. The only time where we don't have any possible solution, if you are facing the sun directly, let's say that, I mean, you are driving your car, VRC experiment, toward the sun, and the sun is actually coming directly into your photodetector, I mean, there is nothing you can do, okay? Because basically now you go to the saturation region, so that blinds the photodetector. I mean, look, so just consider it like as an analogy. I mean, like you are actually looking at the sun with your eye. I mean, without a sunglass, okay? That basically blinds you, right? I mean, it's the same story, okay? But of course, I mean, the possibility that you actually end up with the direct sunlight is quite unlikely, and to actually kind of reduce the effect, you can still use some type of filters, perhaps.
Thank you very much for the opportunity.
One more question.
Hello, Murat. I was going to ask for coherent modulation, we use more resources, and for power-based system, it's much simpler to implement. So how is the data rates compared?
Of course, I mean, with the coherent modulation, the data rates are much, much higher. Because you now have the flexibility of using like the more complex advanced modulation techniques such as the PSPA, QM. So again, for example, in our recent experiments, we were able to achieve like 256 gigabit per second with the coherent systems, okay? But in the IMDD systems, basically, I mean, the data rates are relatively lower. But again, it is not just about the data rate comparison. I mean, coherent systems are also able to support longer transmission distances because now you have actually that local oscillator in your hand. So therefore, the responsivity is actually increasing. So that is also the same reason why in the space, all the intersatellite links or space links, the people actually prefer to use the coherent systems.
Thank you. Is there anything else?
Hello. My question is regarding the wavelength design. So, since by using Hamilton symmetry, the spectrum is reduced by half. So I was thinking of, or rather, I have seen that instead of using Hamilton symmetry, they are using multiple LEDs and PDs. But I was curious, like how cost-effective is comparing to Hamilton symmetry by using multiple LEDs and PDs.
I mean, that's a fair question, of course. I mean, like when you use these like the modified versions of the OFDM, I mean, you are sacrificing from the spectral efficiency. So, I mean, actually half of the spectral efficiency is gone in the DC bias optical OFDM. In the AC OFDM, the thing is actually even like the more, let's say, even like I think, yes, I mean, it is reduced to the like a fourth of it. So, I mean, it might not be the best possible solution for the spectral efficiency. For your question about the multiple LEDs, yes, it is possible to use them, but I am not sure how they are related to this problem because the reason that we are using optical OFDM, because I would like to actually mitigate the effects of the frequency selectivity. That is the reason that we prefer OFDM. But for example, you can use single carrier frequency domain equalization or some time domain equalization techniques if you want. So therefore, you can actually kind of avoid the problems of which is arising from the implementation of the optical OFDM. So I think those might be better solutions.
Maybe I just wouldn't put it bad, but I have seen that instead of using Hamilton's method, they are using real imaging separator. So they are sending the real part and by imaginary part separating with like negative and positive part. And with negative part, they are getting the amplitude of the negative part and sending with sending each of the part with different LEDs.
Okay. Now I understand what you meant. I mean, I don't remember the details of that paper we are referring to. I mean, so to be honest, I mean, I cannot give like a one-to-one comparison which one will be better, but I understand your point. Actually, I gave just two examples. You also provide another way to actually handle the selectivity. There are many other methods. To be honest, I mean, which one is better than the other one? Probably it depends on the computational complexity as well as the some other factors. But for example, again, in the standardization, they simply went ahead with the DC-based optical OFDM, not because it was the best one, but because of the some other reasons related to the manufacturing.
Thank you.
I wanted to ask about what are the challenges that you face in your experience? I mean, what are the challenges of the BHC systems?
Actually, I think the biggest challenge that I face in the VLC or in general optical wireless is not actually technical. It is non-technical. Okay, because it was very difficult to convince the RF community about the benefits of the optical wireless. Because as soon as they actually hear the term optical, they think that, oh, okay, I mean, this is not wireless, let's stay away from it. So, I mean, that is my honest answer. But I think after 20 years, the things have been changing in a more positive way, especially with the recent commercialization success of the FSO in the space domain. Now there are many, many companies in the market. And I believe that in the next 5 to 10 years, you will actually hear the term VLC FSO even more. And hopefully some commercialization successes will also follow.
This challenge, and you mentioned that phase-based optics solve the interference. So, is it solve the interference completely?
Yeah, I mean, just imagine like a directional optical link, okay? Because how do you actually end up with the interference in the RF systems? Because they are kind of broadcasting in nature, right? So if there are two neighbor stations, I mean, like it is possible that they interfere with each other if you don't do like a careful planning. But in an FSO link, I mean, you have directional, so therefore it is point to point. So therefore, there is no interference that can actually come from those type of two point-to-point links.
Murat Hocam, thank you very much. It was a great presentation. Always a pleasure to have you in our conferences and meetings. You're welcome to stay, your students' presentations as well. So we'll have a picture. Maybe Murat can also be in the picture. Right? Yeah. Okay, maybe we can just fit in also. If you guys can come here all together, and just leave a room for Murat as well.
Hüseyin Hocam, Orkun Hocam çok teşekkürler davet için de. Resim için de çok teşekkürler. Güzel bir an olacak benim için de.
Biz de teşekkür ederiz. Okay, you guys can come over here. Okay, some of you can step here, some of you can be down. All together, just leave a gap for Murat as well. We can also have